looking at the real the algebra SL2C. That's what, and from now on, it will be always, I would always write SL2C. And this is joint work. I will talk about joint work with my PhD students, Florian. And I will just start by stating the result that we obtain. So if you start with the Poisson manifold, M pi, I will always denote it like this, and P a point on M, such that pi vanishes at P, and the isotropy algebra at this point P is isomorphic to SL2C. Then we proved that then there is a Poisson diffeomorphism are denoted capital Phi, going from a neighborhood of the point U inside M to the linear Poisson structure on the dual of SL2C. So to V inside C, where this V is an open neighborhood in the dual of the Lie algebra, such that phi of P equals 0. So this is basically for if I would replace here SL2C by a compact semi-simple Lie algebra, this would be Con's theorem. So we basically prove Con's theorem for SL2C.
Ioan?
Yes.
So sorry, I already have a question. Does it mean you are doing this stuff in the smooth category?
Yeah, so for me, everything what I'm doing is in the smooth category. I'll make a few comments about things which are outside of the smooth category. Mm-hmm.
Thank you.
And yeah, so basically this is my plan. I will start by telling you a little bit about the background of this problem, and it all started with this paper of Alan Weinstein on the local structure of Poisson manifolds, where these problems of linearizations were first posed. And I'll tell you a bit what the status of the problem is in the smooth category, especially, and also in the analytic category. And second and third, I will tell you a little bit about the proof. And the proof involves two ingredients. The first one is that we actually calculate the Poisson cohomology of SL2C. And the last point is the proof of the theorem, which uses analysis. It's a proof very similar to Con's proof of Con's theorem of linearization. And it is based on this Nash-Moser-Fast convergence method, but we had to change this method a bit and adapt it to the setting of flat functions. So this is what I want to discuss in the last part, how these adaptations went. Okay, so I will start with the background. Well, I mean, the background is, think about that you start with any Poisson manifold M pi and a point P on M, and you want to understand the structure of pi around P. And the first thing that you can do, you can look at the Taylor series, or the Taylor series of pi at P, and of course, this makes sense as a Taylor series if you choose a chart. And I'll denote it like this. So I'll denote it like the infinite jet of pi at a point P, right? And this is a term pi 0, which is a constant bivector field pi 1, which is a linear pi 2, and so on. So each of these terms pi k is a symmetric function of degree k on the tangent space at P, wedge 2 TP. Okay, so maybe I should put here a star depending how you define symmetric powers. Okay, so this will be the Taylor series, and then so you look here and start comparing the two things. And first, you can look at the first term of the Taylor series, and this is basically just the value. So the 0th term is just the value of the Poisson structure at that point, and that you know how to get rid of it by one of the first results in this paper of Weinstein, which is the so-called splitting theorem. So the splitting theorem tells you that you can always find coordinates around the point P which split off the constant part. So you can decompose P into a sum of two Poisson structures such that the second one, theta, vanishes at 0. And then if you want to understand, so you basically restrict to this transverse Poisson structure, and then you get rid of the first term. So I'll just erase it from here and also erase this splitting theorem if I manage to, yeah. Okay. Right. And then the next term that you have in the Taylor series is the linear term. And this linear term is what is also called the linear Poisson structure. So pi1 is a linear Poisson structure in the sense that the coefficients of the bivector field are linear functions, and such Poisson structures are in one-to-one correspondence to Lie algebras. So here is explicitly, in this case, the Lie algebra G on the dual of the cotangent space at P, and you can write in coordinates the Lie bracket. The structure constants of the Lie algebra will be precisely the constants that appear here in the bivector field. And a converse construction which starts with such a Lie algebra G and gives you a linear Poisson structure, this is called the KKS Poisson structure. So the linear Poisson structure corresponding to G, which I will denote by pi G. So if I move back here, the first term, I think about it as, let me write it pi G. So this is the linear Poisson structure corresponding to a Lie algebra. And this Lie algebra G is, as I said before, the isotropy Lie algebra at P. Okay, so if I go on, well, the first question which you can pose is to compare these two Poisson structures. So you might wonder if you can find a local Poisson diffeomorphism between a neighborhood of this point P and a neighborhood of 0 in the dual of the Lie algebra. So to a diffeomorphism which would linearize the Poisson structure. And following basically the terminology from Alan's paper, we call a Lie algebra Poisson non-degenerate the answer to the question is always yes, meaning that whenever I take a Poisson structure which vanishes at a point and its first order jet is the linear Poisson structure corresponding to the Lie algebra, that it is linearizable. So the answer is yes. Okay. And well, this is also the part in the title of the talk about what Poisson non-degenerate means. So the result that we prove basically says that this SL2C is a Poisson non-degenerate Lie algebra. And if you start wondering which ones, I mean, you can start looking in low dimension. In dimension 2, there are two Lie algebras, an abelian one and a non-abelian one. The abelian one is degenerate. There any Poisson structure which vanishes to order at least 2 at a point will have the abelian Lie algebra as the linearization, and and the non-abelian one turns out to be non-degenerate which is not very hard to prove. And also in dimension 3 and 4, this was studied in the book of Dufour and Zung. You can find most, I think most cases are being treated. But following again Alan's paper from '83, one of the first things that he tries is basically to find a formal linearization. So maybe you can't solve the problem directly in general, but you start you start to solve it at the level of the power series, right? So that means to find, let's say, an infinite jet of a diffeomorphism at 0. I'll write it as identity plus phi1 plus phi2 and so on. So this is the infinite jet of a diffeomorphism, such that if you apply this jet to the infinite jet of the Poisson structure, so to pi g plus pi 2 and so on, you get pi g. And you can start looking at this equation term by term, and you have to solve all kind of equations recursively. And then Alan also proved that in the same paper from '83 that, well, you can always do this if G is semi-simple. So this works if G is semi-simple. And the argument is that all these equations that you solve step by step are cohomological equations in the cohomology of this Lie algebra. So, and you basically use the fact that for every semi-simple Lie algebra, you have the cohomology of G with values in any finite dimensional representation. So for us, what is important here will be symmetric powers of the adjoint representation. This is always 0. This is also called the Whitehead, or by the Whitehead lemma. Okay, so you can solve this and you can find this infinite jet, and you can always reduce the problem to, well, you can always formally linearize Poisson structures. And Alan also conjectured that this would be, that one can do this also in the analytic category. So if you start with an analytic Poisson structure, that this procedure could be made to converge, that you actually find a diffeomorphism, which, an analytic diffeomorphism. And this was proved by Jack Kahn in 1 year later. So this is '84. So this works also in the analytic category, and again for G semi-simple. Okay, but in this talk I will be mostly interested in the smooth setting, and for that I will write. So sorry. So before I wanted to say one thing. So somehow, and in the semi-simple case, so we're basically looking at a Poisson manifold with a 0 where the isotropy Lie algebra at that 0 is semi-simple. And then by Alan's result that I mentioned above, we may assume that pi equals pi g up to infinite jet. So the infinite jet of pi at p is just a linear term, right? And we'll try to see how if pi is actually diffeomorphic to pi g. And so in the semi-simple category, I will explain a little bit what is known and the classification of which Lie algebras are Poisson non-degenerate or not is done in terms of the real rank of the Lie algebra. which is the dimension of the A component in the Iwasawa decomposition. So this is the real rank. And the first such result was due to Kohn. So in when dimension of A is 0, so in that case, the Lie algebra is Poisson non-degenerate, and this corresponds to the case where G is a compact Lie algebra. So this is compact semi-simple Lie algebra. And this was proven by Kohn in 85 with an analytic proof. And also conjectured by Weinstein in the same 83 paper. And Kreinig and Fernandez gave also a geometric proof of this. Result. Okay. Then the next case is when this real rank of A is larger than 1, so at least 2, and in this case, this is not what I wanted. In this case, the answer is negative. So these Lie algebras are Poisson degenerate, and this is a construction also due to Allen from a paper in 87. Right, so it's basically the construction of an explicit flat deformation of these Poisson structures, which is non-trivial. And the case, the case of real rank 1 splits into two subcases which seem to be different. So the first subcase is when the K component is semi-simple. So the compact part in the Iwasawa decomposition is semi-simple. And in this case, it's also not Poisson. It's also Poisson degenerate. So Poisson structures are Poisson degenerate. And this was proven by, well, in the case of SL2R, this was proven by, this is the lowest dimensional case, and this appeared in this paper of Allen from 83. And the general case was done by Monnier and Zung. And the only place where I could find it is in this book by Monnier and, by Dufour and Zung on Poisson structures and their normal forms. So that book is.
Sorry, Ioan, just a stupid question.
Yeah.
For SO2R, like K is SO2, isn't it?
So.
Right. So
yes.
But then, like, how semi-simple is SO2?
Maybe you mean not semi-simple.
Exactly.
Yes.
Thank you.
Okay.
It's not semi-simple, sure. But maybe this is good also to explain this case. So SL2R, so K is, I'll just write it here. So SL2R, here K is SO2, A are matrices of the form lambda 0, 0, minus lambda, and N are nilpotent matrices. I'm at the margin. All right. Okay, and I also prepared this nice, a drawing for the SL2R case. This is basically what the deformation that Allen describes in his paper. If you look at SL2R, what I drew here is the symplectic foliation on the jewel of SL2R, which are the fibers of something like R squared minus Z squared. And this deformation that he built, so I call it pi, will be this pi SL2R plus some W, where this W is supported outside of the cone. So the support of W is in R larger or equal than Z. And then the effect of this is that the outer leaves, which were these one-sheeted hyperboloids, they start spinning around the cone. So each such leaf spins and converges to the cone. So this is the construction in Alan's paper for SL2R. And so the remaining case is when K is semi-simple. This is unknown in general, and this is what we prove with Florian. So we treat the lowest dimensional case, SL2C, and for this one we prove that this is indeed Poisson non-degenerate. Okay, so I'm getting now to the second part, which is about the Poisson cohomology of SL2C. And I will explain basically what the Poisson cohomology of SL2C is. I will tell also a few things about the proofs, but not too many. So first of all, I will identify always SL2C with SL2C star via the trace form, and I denote the Poisson structure just by pi. And the first or the zeroth Poisson cohomology group, these are the so-called Casimir functions, or functions which are smooth functions which are constant along leaves, or invariant functions. And these are quite easy to describe in this case. So you can prove that H0 SL2C pi is the zeroth Poisson cohomology is isomorphic to C infinity of C. I will write it like this, where this map goes as follows. So if you take a G here, you precompose it with a function f, which is invariant on SL2C, and this function f is nothing but the determinant of a matrix, viewed as a map now from the Lie algebra SL2C to C. And basically, so this function is constant along the leaves. Of course, the determinant is invariant under conjugation, and you can also use it to describe the leaves quite easily, and I will also do that. So the symplectic leaves are, so first of all, for Z non-zero, you have the fiber of F is a symplectic leaf. I will denote it by L index Z. And this is diffeomorphic to a cotangent bundle of S2. And for Z equals 0, F at -1 of 0, this is the nilpotent cone inside SL2C, and this decomposes into two leaves. So one is, I'll call it L0, and the other one is just the set composed of 0. And this L0 you can also write down its diffeomorphism type, and this is basically the cotangent bundle of S2, out of which you take an S2. I will use to some extent, well, I will use these things a bit later on. Right, so this is the zeroth Poisson cohomology of this Lie algebra. And before I talk about other groups, so let me say that let me introduce just a couple of things. So somehow, well, Poisson cohomology I'll denote it always by h dot of m and pi, and this is the Poisson cohomology. This is the cohomology of multivector fields with differential d pi. And then if you fix a point, you have two other flavors of this Poisson cohomology. So the first one I call flat Poisson cohomology at p, and I will denote it by h star p of m and pi. And this you obtain by computing the cohomology of a subcomplex. So the subcomplex is the complex of flat multivector fields at p. So these are W multivector fields on M, such that if you calculate the infinite jet of W at a point P is 0. So the value of W at P is 0, and all its partial derivatives is 0. And the formal Poisson cohomology of M at P is, I will denote this by H star of F of P of M and pi, and this is simply the cohomology of the quotient complex. So these are multivector fields on M modulo flat multivector fields on M. Right, so this is basically, well, formal power series of functions, tensor multivector field, or tensor the exterior algebra of Tm at P, and then the differential is encoded precisely by the infinite jet of pi.
A naive question: if you know the flat one and the formal one, can you recover the full Poisson cohomology?
So in general, I don't know. In general, of course, you have two complexes, and one is the quotient, so you will have a long exact sequence in cohomology, and I don't know what that boundary map does in general. But in our case, this is of course the case. The boundary map will be trivial, and basically this holds for every semi-simple Lie algebra. So if G is a semi-simple Lie algebra, you can prove that the Poisson cohomology of G star by G always splits, well, non-canonically, but it splits into the, let me just write formal at 0 plus the flat Poisson cohomology at 0. And second, the formal one you can calculate. The formal one is basically an algebraic problem, and you can use their Lie theory, and you can prove that the formal Poisson cohomology at 0, oh, let me better use the notation that I had before. So formal at 0, this is the Lie algebra cohomology of G, so the Chevalier-Eilenberg cohomology of the Lie algebra, tensor the formal invariant functions, which you can also prove that these are always spanned by some, well, generated by some polynomials. So these are formal power series in Q functions, which people, well, those F1, Fq are homogeneous polynomials, and Q is the generic co-rank of the Poisson structure, basically.
Units, do you need some G to be semi-simple for 2 to hold? Hi.
Say again, sorry?
Do you need G to be semi-simple for 2 to hold?
Yes, yes.
Okay, so I wasn't sure if it's just...
Or okay. I'm pretty sure. Right. And I'll give this, so for SL2C, in our case, the Lie algebra cohomology has 2 generators, both are in degree 3, and this formal invariant functions have 2 generators, which are precisely the real and the imaginary part of this function f, which is kind of logical because that's also how the invariant functions work globally. So somehow what we are left here to do is calculate the flat Poisson cohomology. So this is the big question of this SL2C pi, the flat one. And the flat one, we'll see that actually it has kind of a different behavior than the formal one, in the sense that it even lives in other degrees. Right. And for that, I will talk a little bit about the foliated cohomology, and then I'll go to the flat foliated cohomology. And this will be an ingredient which will help us describe the Poisson cohomology. So the foliated cohomology, well, it's something you can associate it to any foliation. For me, I will look at SL2C minus 0. So this has the symplectic foliation is regular outside of 0. I'll denote this by F. And the tangent bundle of F can be given either, well, it's the image of pi sharp, or it's also the kernel of this df, this Casimir, or you can also write it like this. So this is also useful to write. So of course, here I'm basically also telling you that F is a submersion away from 0. Okay. And the complex are forms on F, so the exterior powers of T star F, and the differential, you can think about the differential as being a leafwise de Rham differential. And from this, you obtain the foliated cohomology. So H star of F. And the way to think about this space, so the way to imagine it, is basically thinking about it. It is made of smooth sections of a vector bundle over C. Right, so, and the vector bundle is basically at the point Z in C. I mean, I use C here because C is the leaf space. And at the point Z in C, you look at the cohomology of the leaf above Z, so LZ, right? But of course, this interpretation is a bit problematic because this is not really a smooth vector bundle over C, and simply because these leaves, I described them a bit earlier, how they look, what their diffeomorphism type is, and basically they are homotopy equivalent to most of the time S2 when Z is non-zero, and at Z equals 0 is actually an S3 for Z equals 0, right? So this is not really, I mean, it's hard to make sense of it as a vector bundle, but if you remove this L0, so the singular leaf, everything works, right? So this works if we restrict to SL2C minus F at minus 1 of 0, right? So F maps this to C minus 0, and then we have this vector bundle H2. So H2 or H, well, let me just write the fibers, right? So the fibers are the cohomology of L something over C minus 0. Right, and what I'll be interested in is basically the second cohomology, because the other ones are trivial, and the interesting thing is that this bundle H2 of L dot over C minus 0, this is a non-trivial line bundle. right? So real line bundle, and well, it's a line bundle because this S2 are cotangent spaces of spheres, so they are just one-dimensional, right? So if I'll try to make a picture here. So this is C. We remove 0, and what happens is that if I basically go around 0, do such a loop, then I can lift this loop, let's say, with a connection to a diffeomorphism of L1, and I'll call this, let's say, tau from L1 to L1, but in cohomology, this tau star will be actually minus identity from on H2 of L. Okay, of L1. This is not a problem, but I just want to point out that this bundle is non-trivial. So if you want to describe its sections, it's not going to be just one fixed sections times smooth functions on the base. And you can describe its sections by looking at two basic sections. So first of all, this is a symplectic foliation, so it has omega 1, which is the leafwise symplectic form on F. And so this is the symplectic form on the leaves. And you can also build an, I'll call it omega 2, which is the pullback of omega 1 by multiplication by I. Okay, this is one description of this 2 form. And multiplication by I preserves the foliation, not leaf by leaf, but it preserves it sends leaves to leaves, and then you can pull it back. And this is a second symplectic form. In fact, what happens is that this Poisson structure that on SL2C, there is also the complex Poisson structure. And that one has a real and an imaginary part, and this omega 1 and omega 2 come from that real and the imaginary part.
That's a naive question, Units.
Yes.
So I mean, you have a regular foliation. So I mean, in terms of foliation holonomy, since it's the fiber of a submersion, it's going to be trivial holonomy. So how do you rectify that with the fact that you're getting a non-trivial element in H2 of the leaf space here?
So this map here goes transverse to the leaves. This is not a holonomy. What I'm doing here is the leaf
I see.
space,
Yeah.
and you go on.
Yeah.
So yeah.
Yeah. Thanks. Sorry.
H2. Right. So you have these two elements, and you know that at every and actually they span everything at every point, right? So you can kind of describe sections with them, but then they vanish in places. So omega 1 vanishes on this half line, and omega 2 vanishes on the other half line. Okay, so this is a little bit to give an a geometric interpretation, and then they and because they are 2D and they are both sections of a line bundle, you do expect them to satisfy a relation, and I wrote here the relation between them. Right, so these two as sections, they are still coupled like this in H2 of F. Okay, so here I talked about F, and actually everything worked when I took out F0 for 0 and then F0. But for me, what is interesting is also to look at 0, and what is interesting is what I call the flat foliated cohomology. And so you should think about this as being foliated forms on SL2C, which vanish flatly at 0. Now, the problem is that the foliation does not extend at 0. So it's kind of hard to talk about them, to define them in this way. So I just wrote an explicit model for this flat foliated forms, which, if you look here, so this is something you could do for any actually unimodular foliation. You can calculate the cohomology of a foliation using a subcomplex of the de Rham complex. And right, so a form here, if I think about the form omega1 here, if I multiply it with or omega, if I multiply it with df1 and df2, it only, so the only thing which survives is basically its restriction to the kernel of f1 and f2, and this is why you can view this as a foliated form. And the fact that this df1 and df2 is closed, it means that basically the differential that you have is the de Rham differential. So the flat foliated cohomology we just define like this, and this is something that we managed to compute. So this is what I want to describe next. So in degree 0, I think, well, as expected, and this basically follows from, well, in degree 0, this is kind of easy. These are smooth functions on C, which are flat at 0. So whenever I put this index 0, it means flat at 0. And the map is exactly the same as before, right? So G goes to G composed with F. So in degree 2, this will be sections of this line bundle, which is twisted, but we still wanted to write them somehow algebraically to have representatives. And then you can write it like this. So it's 2 copies of C infinity of C modulo a submodule K. And the map here, since G1, G2, or the equivalence class of G1, G2, is sent to G1 composed with F omega 1 plus G2 composed with F omega 2. I'll tell you in a second what this G is, but I just want to make here a remark. So this omega 1 and omega 2, they actually kind of explode at 0, but they explode in a controlled way. And here we're multiplying them with functions which are flat at 0. And this is why the whole operation in the end is actually well defined, and it's actually flat at 0. So they can be like this. And this K, well, you can write it down quite explicitly, the submodule. So here is a description, and this relation that I wrote here is basically dual to the one we had before between omega 1 and omega 2. Okay, I think this is less. And all the other degrees are 0. So, okay, not 0, 2. Okay, so this is the flat foliated cohomology of this foliation. And now what happens is that when you calculate Poisson cohomology, you can also look at multi-vector fields that are tangent to the foliation that forms a subcomplex. And for a regular foliation, that is isomorphic to foliated cohomology. And now if you put this flat at 0, this two also correspond. So this theorem gives us basically the so-called tangential flat Poisson cohomology. And that can be further used to actually calculate the Poisson cohomology using a spectral sequence. And then, so using this result, we managed to calculate the Poisson cohomology, and I will just give you the result in terms of the flat cohomology. So the Poisson cohomology is isomorphic to, well, 0 or H0, so these are flat Casimir functions, or H2, which is this twisted module, and the degrees are written here. So in degree 0 and 3, it is isomorphic to H0, and in degree 1 and 4, it is isomorphic to this H2, right? So the degree 1, it means that, well, there is a rank 1 module of automorphisms, of non-trivial Poisson automorphisms. And these were actually constructed in one of the papers of Allen, this automorphism. So they appeared before in the literature. Right. And what is important, and also if you look at the degrees, so for example, 1 and 4 are degrees where there was no formal part. There was no formal Poisson cohomology. If you compare it to the formal Poisson cohomology, 3, there was formal Poisson cohomology, but that one had somehow rank 2 over the formal power series. Here is just rank 1, and 6, and in degree 6 there was formal, but there is no flat one. I think this is also kind of interesting to point out. How am I doing with time? Okay, so let me now make a remark, because now I'm moving a little bit towards this analytic proof. And first, this fact that H2, so for us, what is important is that H2 flat Poisson cohomology is trivial. And the fact that this is trivial is also equivalent to the fact that you can construct homotopy operators for the Poisson complex in degree 2. So these are linear maps going in the other direction, H1 and H2, which satisfy this homotopy relation. Okay. What I wrote here is basically a triviality. This holds for any chain complex. So if you have a chain complex with 3 terms, there will be no middle cohomology if and only if the chain complex is homotopic to 0, and then you can build this. But what is important for us that we actually build this H1 and H2, and they are built in the proof of the theorem. And they also have some interesting properties which are useful. So we obtain H1, Hi. First of all, they are, I wrote here semi-locality, that they are semi-local. By that, I mean that they induce homotopy operators on, these operators are not local operators. They are not differential operators. They are obtained by integrating, they are pseudo-differential operators. But they do restrict to balls of radius r for every r, in the sense that, well, if you take a multi-vector field on a ball of radius r, the value of h, if you would extend it, the value would depend only on the restriction, right? So you have here induced homotopy operators, which imply also that the Poisson cohomology of these balls is trivial. And here it's important also what distance you take, so that these are the balls with respect to the inner product that you obtain from the Cartan involution and a killing form. Okay, so this is one property, and the other property, which will be very important, are that these homotopy operators satisfy certain continuity. So that they satisfy certain inequalities that I will talk about later. Okay, and this brings me to the last part of the talk, which is the analysis part. And here I'll go a little bit faster. So what we do, we kind of try to copy Kahn's theorem, Kahn's proof of the analytic proof of the linearization for compact semi-simple algebras. And Kahn's proof uses what is called the Nash-Moser method. So basically you start with this equation that you want to solve. So let's say the push forward of pi g along phi is pi, where the unknown is this phi, the diffeomorphism, and you want to solve it. And then you kind of don't know how to solve it, but you apply Newton's method. So you applied Newton's iteration to solve it. And then Newton's method will tell you, will give you a sequence which will converge to such a phi. And basically you start with pi 0, which is pi, and then you correct it to bring it a little bit closer to the linear one. And you correct it by taking the flow of a vector field xk at times 1. And I use here pullbacks instead of push forwards of pi k. right? So this is how you correct, and this xk to actually obtain somehow the infinitesimal correction will be given by applying the homotopy operator to the difference, pi k minus pi g. And the final diffeomorphism will be obtained by composing all these flows. So you take x0, compose with flow x1, and so on, and this will solve the equation, right? So this is basic. This will be the algorithm that you would obtain by following Newton's iteration. Now, in practice, you have to first of all be careful that these pi k's are defined well, where they are defined and where the flows are defined. So in practice, in this algorithm, you'll work with walls of a certain radius, which will decrease while you run the algorithm. That's one part of the problem, but then you also need to prove some inequalities. So for that, you'll need this H1 and H2, the homotopy operators that you have for Poisson homology, so H1 and H2, they also satisfy inequalities of this form. So somehow the kth norm of Hi of something has to be bound by.
Ioan?
Yeah.
Just a naive question. You're in the algorithm, we're only using H1. Why do we need an estimate on H2?
To obtain the estimates in the iteration.
Okay.
In the definition, not, but you need it for the estimate. Mm-hmm.
Okay.
So you also need it. All right. So and here you see that, well, this A is fixed. So somehow you're allowed to. So these are the CK norms measuring K derivatives, and you're allowed. So this would be the classical Nash-Moser technique. And then second, if you actually do this procedure, you'll obtain somehow recursive inequalities. So this xk plus 1 will be smaller. I mean, you obtain some sort of iteration which goes very fast to 0, but the indices of the norms that you're using will always grow. So it will grow and grow and grow. So in the end, you can't do much with it. But then Nash came with the solution, which was using this so-called smoothing operators. So the smoothing operators are some maps from sections of a vector bundle. In this case, they are multi-vector fields to itself, which approximate the identity arbitrarily well. So they depend on a parameter t. And when t goes to infinity, they approximate the identity very well, but they are smoothing in the sense that they even induce maps from continuous functions to smooth functions. Okay, so it's in some people will also known this as modifiers in PDEs, and or you can think about them as being approximations of the identity map by compact operators. These are other ways of seeing them. And then the way you correct the algorithm for it to work, it's basically putting here somewhere the smoothing operator. So as tk, where this tk is a sequence that you have to choose such that everything works. It's usually a sequence that goes to infinity double exponentially. Okay, and now, so now we want to apply the same procedure to SL2C, and I want to explain a little bit what the problems were that appeared when trying to do this for SL2C and how we solved them. And because I think also that you could apply the same techniques in many problems where you have to deal with flat functions sometimes. So the first problem is that our homotopy operators that we build, they don't satisfy the inequalities that we need. We obtain inequalities where, so this k, we don't obtain a fixed step, but something affine. So lambda times k plus a, where this lambda is kind of big. I wrote there larger than 2 because for lambda between 1 and 2, there is a paper in which they showed that you can still save the problem and you can still do Nash-Moser if lambda is between 1 and 2, and this will be important later on, right? So this is the problem. And then if you look where this comes from, so why do we get such bad inequalities? They basically come from the fact that on flat functions, you can divide by powers of x, of the norm of x, right? So if you have a g in here, you can define g divided by x to the power m. And because g is flat, this will be smooth at 0 and again flat at 0. And when we were doing this calculation, we were bounding these terms by this. So you take this g divided by norm of x, and you want to calculate its nth norm, let's say. And then you write the Taylor, so you expand g up to order m. So you look at the Taylor expansion up to order m of g, and use this formula with the integral reminder, and then you can bound this by norm of g index n plus m. Okay, so this is something that we were kind of using all the time. And then we decided, okay, let's try not to use that. And then we introduced some new norms here, which I'll call, I don't know, G with two indices n and m, which do exactly what our problem was. I mean, solve exactly what our problem. So they are basically the norm of G divided by x to the power m, n. So we have these new norms, and on flat functions, which depend on two indices. And this they give the same topology, final topology on, in the end, they give the same topology on C infinity m, because by what I wrote above, they lie between the n plus m norm, and it's also Gn. So here, I should have taken here the maximum with respect, let me put here k, sorry. I'll move this a little bit. And this should be the maximum when k is larger or equal than, smaller or equal than m, this norm. Index k, and then, so they lie between the norm n and the norm n plus m somehow. And for these operators, we managed to prove that for these norms, the homotopy operators satisfy now inequalities of this form. So the norm of index n plus m, hi, in the first term, we just get the translation. And in the second term, we get something which a priori looks kind of bad. So it's m plus b times n, so you get here an affine factor, but which comes only from the first one, and then another translation. But then the thing is that you can now do, so you have these two indices, and you can do something like, you can look at other norms which are indexed by n and p times n, where n is kind of large. And then for those, we'll obtain this type of inequalities, which we can apply this modified version of the Nash-Moser technique. And yeah, so this was one of the problem. And the second one is, and I'll just write it here, and I'm not going to explain it too much, is the fact that we also needed to build smoothing operators on the space of flat functions. So this was also technically not, well, I couldn't find it anywhere in the literature. before. And so basically we have two families of smoothing operators, one in each for the second norm and in each index of the norms. And in the second index, so this is just divided by x to the power m, they are very easily built. So you just multiply with a function which is 0 around 0. But the other ones are kind of more complicated, and also the inequalities that we get are not the usual smoothing inequalities, but they are still good enough for us for everything to work. And yeah, so the second ones were a bit more complicated to build. Now I will stop here. The only thing what I want to say is that this second part, the analytic part, we could apply to any Lie algebra as soon as we have homotopy operators on the flat complex satisfying these properties. So for the remaining of the semi-simple Lie algebras, we hope very much that the only step that we still have to solve is the part about cohomology. Okay, I'll stop here. Thank you.
Okay, thanks a lot. So please, questions or comments? I have a very simple question. So, like you considered that example of SO31. Like, what's the next example? So, what are the what would be the hierarchy then in complexity of the next ones, and why constructing a homotopy or whatever, or what you're saying? This computing of this flat homology, right? That's what's specific about it. That's the structure of the leaves that you understood so well.
So I think, well, in the case of SL2C and also SL2R, somehow we were kind of lucky that the foliation is regular outside of 0. So we could work with things that are flat at 0. In the other cases, I think we'll have intermediate degeneracies, and maybe we'll have to look at things which are flat along submanifolds of lower rank. And they're also.
But what's the next example?
I don't know.
Oh,
I don't know.
Okay, that's honest. So there is on the chart Dima's question. Dima, do you want to ask it or?
Yeah, I think he just answered it.
Yeah, probably. Like
in the course of answering your question.
Mm-hmm. Okay. Okay.
Thank you.
Any other questions or comments? Maybe then I have. Yeah. Oh, go ahead.
So when you say that the part about cohomology is what's missing, do you have at least a feeling about whether it's more that it's harder to describe cohomology or that it might actually not have these homotopy operators?
So I always believe that when you can actually prove that some cohomology is trivial, if you look at that proof, you'll be able to construct the cohomology, the homotopy operators by going through that proof. How good they are, here we obtain some which have this form. Well, to be honest, we did not look yet at other examples very clearly, yeah, I don't know this.
Okay, thank you.
Yeah, more questions or comments?
Maybe this is too general, but I mean, is there any conditions you can put on a Lie algebroid where you could try to do this, use your techniques to prove something when you linearize you look at the dual of the Lie algebroid, like the linear Poisson structure?
For the dual, there are linearization results for For the algebroids, I think there is by Monnier and Zung. By Monnier and Zung, there is a linearization result which uses the Nash-Moser, and it's still like which I think corresponds to this classical proof of Kohn. But again, it's a case where the isotropy algebra is compact.
Right. So can you use your results to extend these results?
I mean, the problems are about understanding this cohomology, having better techniques to calculate it. I think our techniques worked, but they were also sometimes very ad hoc. So
okay, they're not general enough to apply to. Okay.
There are parts which seem, I mean, that, well, this would work more generally, that we use, I don't know, for example, we use averaging with respect to the compact part of the Lie algebra. That works always, and other things work, but not the full methods, not all the methods.
Okay, got it. Thanks.
So there is this remark on the chart that maybe SL3R in the next example. Do you agree?
I don't know. I don't know. SL3R.
You need real rank 1, right? Or
yeah, real rank. Yeah, Peter. Do you know this? Peter should know this.
I think SL3R doesn't have real rank 2.
Do you know what is the next one? Real rank 1 and semi-simple compact part.
Okay. We don't need to resolve it real time, but well.
So it's got to be SU21.
SU21.
This has real rank 1, and its real dimension is 8.
Okay, thank you.
But yeah, it's not the point.
So any more questions or comments?
May I?
Sure, go ahead.
Yes, what about non-semi-simple Lie algebras, which are non-degenerate in the sense? What's known about those, aside from the two-dimensional example?
I think so in dimension 2 and 3, this is fully classified in this book of Zung and Dufour. In dimension 4, I think there is one Lie algebra for which this is not known. And then I think for GLN, or maybe I'm saying something wrong, or is it F? No, for affine N. It is known that it works in the in the formal and maybe even analytic category, I think, but not in the smooth. It's not known in the smooth somehow. So people have tried all kind of examples like this.
But the technology, is it similar to, well, what you've been using? Is it all like boiling down to computing this flat cohomology, or flat foliated cohomology?
So I think so. I don't know how they do it, but what I was saying is that they are not doing it in the smooth category. They are doing it only in the analytic or formal category, where you don't need to work with these flat functions at all. How is it in your paper, Dima? You also use in this. You also use something about flat functions for.
Yes, but that was that was locally isomorphic to the two-dimensional non-Abelian Lie algebra. So it's just so you just had to think about some global issues there. But I mean, like near a point. That was already a well-known case by then.
Okay, thank you.
Can I ask you one thing?
Sure.
Hi, Ioan. So is there something that you can extract? I mean, this is a bit of follow-up of Timo's question. Is there something you can extract from your methods that would say that under some conditions, the Lie algebra will be Poisson non-degenerate? Like some conditions on the formal and on the...
So if it is formally non-degenerate, and then its flat Poisson cohomology is trivial, but in the sense that you find homotopy operators satisfying those inequalities, then you can apply the second part of our paper.
And do you think that in all examples that are known, these are satisfied?
I would say, in which are known.
Yeah. Certainly, it's satisfied for compact semi-simple, right?
For compact semi-simple, even better inequalities
Yeah,
hold.
sure, yeah.
Even better inequalities. One needs to try more things and see.
Okay, thank you.
I'm kind of optimistic about these Lie algebras, which are almost symplectic. I think there you could calculate things a bit easier by inverting, by looking at forms with singularity somehow. So it's similar to log symplectic.
Okay, thanks a lot. Any more questions? I have one more slightly provocative question. So how is it? So now we have this result for SO31. Does it lead to some interesting examples, or the nature of the result? Right, it's a positive result, but then does it mean there are no interesting examples, or how can one apply it now?
That's interesting. Well, that's a good question. I think, well, the Poisson structures, I think, that appear in nature are analytic. So everything was known since Con in that setting.
Okay, so you don't have any like interesting looking example in mind, which
No.
Okay. If there are no more questions or comments, let's thank Ioan again. Thanks a lot. So we are wrapping up the session of today, and next week it will be Lisa Jeffrey speaking at Global Poisson. So thanks a lot, everybody. Thank you, Ioan.
Okay, thank you.
Thank you.
Bye.
Bye-bye.